Greetings from Washington, D.C. on December 9th, 2013 from my hotel room. Um, Wanted to give you your online lecture. It's going to be split into two parts for week 4. You need to watch this between now and before the midterm for sure. But it is designed for you to look at it on Thursday night, the 12th of December. Wanted to also make sure you were aware that the Blackboard on week 4 has several things more than just the lecture, but make sure you open up the lecture on light. There are other things like a supplemental lecture on chemistry, gives you just the basics from a friend of mine, Randy Holman, who's a graduate in chemical engineering, gives you the basics in chemistry. It will help you, especially regarding stoichiometry, dimensional analysis, mole to mole ratio. So find out there's a couple of problems in there, word problems, to help you understand what I just mentioned. But moving forward, there's also a midterm review under week 4 that will get you ready for next week, which will also be online. The midterm next week will be online. You will be able to go into week 5 probably starting Sunday. I'll have it open. It just depends on how efficient I'll be between now and then, but I'll have the midterm up there this weekend by the evening of Sunday, and you will be able to take the midterm, print it out, not submit it until you're ready to submit your answers on Blackboard. It will all work out better that way. And then I will not see you till after the Christmas and New Year's break on the January 9th, the 9th of January. Okay, just keep an eye on the syllabus, your emails, etc. for any changes to what I just told you. But that should be the case from here to then. Also, the midterm review, backing up, is an assignment. Alright? It is due December 18th. So make sure you do the midterm review. Alright. Lecture on Chapter 5, which is lecture... It's also Chapter 6. It's a lecture on light. Now, we ended up last week on slide 7, which is the electromagnetic spectrum, the entire picture that's worth 1,000 words. So we're going to move on. Notice that light is an electromagnetic wave in the next slide. It has wavelength. It has it has wavelength. It has frequency, and it has a finite speed of 300,000 kilometers per second. Next slide. This is just a commercial pitch to go online if you have access to the Mastering Astronomy website connected to your book. There is a great tutorial titled Lecture Light and Spectroscopy that will greatly help you with this pivotal chapter. If you do not have access to the online portion, that's fine. The book is very adequate as well. Next slide. Light is not only an electromagnetic wave, but also a particle, a photon, a piece of light, which has those precise dimensions: wavelength, frequency, energy, intensity, luminosity, all in that picture, that electromagnetic spectrum picture. Next slide, which also, again, if you go to the tutorial, you'll get a better understanding. You'll gain a better understanding of the electromagnetic spectrum. Next slide. So a question I have for you: the higher the photon energy, next slide, says the shorter the wavelength. Make sure you understand that. Make sure it makes sense to you. Next slide is matter. When we talk about light, we have to also connect the dots. Matter and light connect. Down to the subatomic structure, the nucleus. Within the atom, the nucleus, which is much, much smaller than the actual atom. But the nucleus holds the mass of the atom, the protons, the neutrons, and the electrons also hold a small amount of mass, very small amount. but primarily the mass of an atom is in the protons and the neutrons. Alright, next slide, a little bit of terminology on an atom. Each element has an atomic number, which precisely equates to the precise number of protons in the nucleus. The atomic mass number is an estimate of how much mass is in that nucleus, which is the protons, electrons, and neutrons all together. Primarily, though, it's the number of protons and neutrons. The atomic mass is sometimes called the atomic weight, interchangeably at that level. And also, it's never exact. There's also always a number, point, several decimal places of numbers. Point, blah 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 blah, and the point, etc. The point 64945, whatever's on the right of the decimal, is from the electron. Okay, but you'll see there's three different elements on this slide. Hydrogen has 1 proton, so it's atomic number 1. Helium has 2 protons, so it's atomic number 2. Carbon has 6 protons, so it's atomic number 6. But you'll notice that their masses are different because there's might be no neutrons, or the same number of neutrons, or a different number of neutrons. Okay, next slide. This slide says that there's something called an isotope. If there is a different number of neutrons than protons, like if in hydrogen there's no neutrons, but there's always 1 proton, then it's an isotope. Alright? If it's 2 neutrons in hydrogen, it's an isotope. Alright? It's that simple. Next slide. Amazing. Jeremiah 32:17. Ah, Lord God, behold, you have made the heavens and the earth by your great power and outstretched arm. There is nothing too hard for you. Love that verse. How do light and matter interact? Well, 4 different ways. Light is emitted, absorbed, transmitted, or reflected. Alright? And through this transmission, we can also think of some objects are transparent. We know about that, right? And also, some objects are opaque. Alright? Let's move on to the next slide. There's a picture there. Which one, look at that slide and use those 4 categories of light and tell me what's emitted. I'll give you a hint. The sun emits, and the light bulb in the lamp emits light. But what's transmitted? What's reflected or scattered? What's absorbed? Notice the tree. The trees are green. What does that mean? It means light is absorbed by the tree, except for the wavelength for green. The wavelength for green is reflected or rejected from the tree. Okay, next slide is a thought question. Why is the rose red? Well, the answer is clearly that the rose reflects, and sometimes I say rejects, the red light. Moving on. So in this, we've learned, in this what have we learned slide, what light is. Simply put, is an electromagnetic wave and a photon. And we find light in a complete electromagnetic spectrum. We use different terms for light because of the wavelength, the frequency, the intensity of the light. Alright, so gamma rays to radio waves is the spectrum. And then next slide is matter, how light and matter, they work together. Chlorophyll is a good example of that. How light hits the plant absorbs the light's energy, converts it straight to matter, we call chlorophyll. Chlorophyll rides up the plant to feed the plant. Okay? And leaves store that potential energy in the plant until it is needed, and then it is extracted from the leaves. Alright, so light and matter definitely interact with each other. Moving on, don't get bogged down. The link here doesn't work for you. There's a link on my hard drive to that file. But don't panic. I'm going to throw terms at you, but you can pause this video and go back and forth, refer to your slides and your book as you go. Moving on, learning from light. Well, hopefully we will get you to be comfortable with the light spectra, how we can use light to observe the universe without being there, how we can take light, and light alone tells us many things about objects in space. Light, the temperatures, planets versus stars, etc. Which way are they moving? Toward us, away from us, beside us? And how fast are they moving? How far away are they? Next slide is a great picture to give you an example of what we do with light. Let's take our sun, for example. Now, our sun is represented on this slide as a hot light source. Alright? And that hot light source can shine to the left. It shines all the way around, but if it shines to the left, it's shining in a prism, and that prism is splitting the rainbow, and it's taken a negative, captures the rainbow of colors, but it also captures the left side, the gamma rays, all the way to the radio waves and beyond, okay, to infinity and beyond. Buzz Lightyear. So what you notice there is an analog and a spectrum. A continuous spectrum shows the intensity. The highest part of that spectrum in selection A is a source of light, our sun, without anything in between, shining through a prism. We call that a continuous spectrum, and that colorful strip is called an absorption line spectrum. There's nothing in its way, so there's nothing that is absorbed. Alright? To the right, selection B, we have another absorption line spectrum, but notice that our sun, or a hot light source, is transmitting through a thin cloud of cooler gas. And while it's traveling through that cloud of gas, some of the wavelengths of light are being absorbed. So notice that the absorption line spectrum does not have the entire rainbow. Some locations, little segments, are missing. Those are the wavelengths that are being absorbed in that cloud. But notice just below, to the bottom right of the picture, if I were to take a prism offset from the source of light going through the gas cloud, offset, this is theoretically the light that is being emitted from the gas cloud, the cooler gas cloud. That emission can be put on a spectrum again. We call that an emission line spectrum. So notice, if I put the emission line spectrum and the absorption line spectrum, overlap them, you get the continuous spectrum again. Okay? This is our summary of light spectroscopy. Spectroscopy. How we understand light. Okay, next slide. There is a tool inside that light and spectroscopy tutorial online to let you mess around with this idea of a gas cloud introduced between a star and a telescope, for example. Moving on. Going back to that solar spectrum, our sun's absorption line spectrum, which was the first picture in the chapter. You know, this slide is an example of real astronomical spectra made from a combination of idealized types. Here we have a continuous thermal spectrum from the solar interior, dark absorption lines where the cooler solar atmosphere, or the photosphere, absorbs specific wavelengths of light. Next slide. So how do the light tell us what things are made of? Well, this slide represents the first introduction to quantized energy levels. notice that there's a ground state. If we intensify a wavelength of light, and you notice in the electromagnetic spectrum we also can measure the voltage, the electromagnetic voltage traveling along the wave. And then in electron volts, if from ground state if we intensify it to where the the voltage or the intensity spikes to at least 5 electron volts, it will return back to ground state. But if we reach a second level of 10.2 electron volts, we reach a new state. Electrons and atoms have distinct energy levels, and each chemical element or ion molecule has a unique set of energy levels. And if we increase the energy level, the intensity, to where we reach at least 13.6 electron volts, we can ionize that gas, meaning we can allow the electron to escape the gravitational forces. Alright, we know this to be the case. Next slide is slide 30, I believe, on your lectures. We have distinct energy levels that lead to distinct emission and absorption lines, unique fingerprints for each element. Each element, for this one it's a hydrogen element, you get one unique absorption line and emission line spectrum and energy level output. For hydrogen, each element has their own chemical fingerprint, which is the next slide. Every atom or ion and molecule has a unique spectral fingerprint. Alright? Physics, with our knowledge of algebra and calculus, a little bit of geometry thrown in there, and a lot of help from several different people all over the world, we're gaining knowledge every day just by observing light. It's an amazing... We've learned so much in the last few years, in the last 50 years. Next slide is, again, there's a tutorial to help you understand what I just went through. Next slide, a thought question. Which letter or letters labels absorption lines? And I'll just go through these real quick, and I want you to make sure you understand it. But this question, if you notice the curvature, the curving line up above, and then the absorption line spectrum below, and then multiple choice A through E. The answer to this question is Charlie and Delta, C and D. That's where you show a dip in the continuous spectrum. A dip in the continuous spectrum. Next question is, which letter or letters labels the peak, greatest intensity of infrared light? Well, you'll notice that that answer is echo, E. That's in the infrared, and it's the highest peak in the infrared. Okay? Next slide, which letter or letters labels emission lines? Emission lines, well, that would be alpha, A, because the continuous spectrum is spiking over there, peaking. Alright. Next slide is, how does light tell us the temperature of planets and stars? We use thermal radiation, which is nothing more than light that is moving, kinetic energy, moving the molecules as it connects to the light, giving us temperature. So we all have a thermal signature. You with me? We all have a thermal signature, a heat signature, and so do planets, so do objects in space. So we all have something in common, a thermal signature, and that's what we use. Okay, next slide is, there are two properties of thermal radiation. Intensity is mentioned on that main electromagnetic spectrum picture up above early on, one of the early figures. Now, intensity, it's per area, so it's the amount of power per area, power in watts per area, square feet, square miles, square light years. You know, that's the point. The larger objects can emit more total light even if they are cooler. Okay? So, intensity. Notice that this graph shows us blue, yellow, and red stars. Out of all of the stars that we find in the universe, boils down to these three types that we can actually see with our eyes. And the blue stars are the hottest. They range in the 15,000 Kelvin range. Our sun is a medium or yellow star ranging in the 5,800 Kelvin range. And then the cooler red stars are 3,000 Kelvin. Alright, moving on. So there are plenty of places to go for more information on spectra, but I gave you a link in this next slide. That's an electrical engineer's perspective from a reputable company, GE. Explains it to you in a different way using your eyes to colors that appeal to a person's eyes. Okay, and it's just to help you. In the next slide, using GE's data, you can see that the human visual system responds to the very small part of the electromagnetic spectrum that lies between 380 and 760 nanometers. Alright? However, it doesn't respond uniformly. Okay, moving on, you can see, and I'm going to take a break right after this because we're doing pretty well. In the next slide, figure 1, given the same amount of power at each wavelength, the visual system will sense the yellow-green region as the brightest and the red or blue regions as the dimmest. This is why among equally efficient light sources, a light source that has most of its power in the yellow-green area will have the highest visual efficacy, such as or that is the highest lumens per watt. However, without a reasonable proportion of red or blue in its output, a light source will not be able to render color satisfactorily, and how we see color depends on the wavelengths emitted by the light source, the wavelengths reflected by the object, the surroundings in which we see the object, and the characteristics of the visual system. Our conception of the color of an object is a constantly changing, highly dynamic process. It depends on what colors surround the object, how long we have been exposed to the scene, what we were looking at before, what we expect to see, and perhaps what we would like to see. It's also psychological. Added to that is the fact that about 8% of the male population and about 0.4% of the female population has a color deficiency or is colorblind to some degree. I had a boss that was colorblind, and I had to change all my slides, forget the color coding. Trying to describe exactly what we see is, of course, extremely difficult, since it depends on language to describe what is really in our mind. It is difficult to visualize the color effect in space, and then to specify the necessary object and light sources to make it happen. Alright? Yeah, so there's a whole lot to this. Now moving on, just to show you a little bit more, you have light and pigments. They mix differently to form colors. This is figure 2. And since the human visual system has 3 color sensors, it is possible to pick 3 suitable colors and generate the other colors by mixing these. By convention, the primary colors of light are chosen to be red, green, or blue, RGB, because they produce white light when they are added together. Color mixing of light is called additive. Any 2 primaries of light can be excuse me can be combined to form a secondary color. Magenta, you've probably heard of that. Red plus blue. Cyan is green plus blue, and yellow is red plus green. When a secondary is mixed in proper proportions with its opposite primary, the resulting light will be white. Therefore, any primary color is considered to be complementary with the secondary color produced by mixing the other two primaries. Yellow and blue are complementary colors of light, as are cyan and red, and magenta and green. In pigments, however, a primary color is defined as one that subtracts or absorbs a primary color of light while transmitting or reflecting the other two. For example, the pigment that absorbs red light and reflects blue and green would be cyan. So the primary pigment colors, sometimes called subtractive primaries, are cyan, magenta, and yellow, the secondary colors of light. The color appearance of an object or surface clearly depends on the light used to illuminate it. Often daylight is considered a standard, but it is obvious that the color of daylight changes with the position of the sun in the sky, how cloudy and overcast it is, and also which direction of the sky we're sampling. For example, northern sky or southern sky. In warm or how cool a lamp, in specifying a lamp color, you'll have to worry about how warm or how cool it is. And in your selection, this is generally a subjective decision. You know, some people like incandescent, for example, versus fluorescent. I like incandescent much more than anybody would like fluorescent. The color temperature of the lamp in kelvins specifies the degree of coolness or warmth of the light source. Another color rating of lamps is the color rendering index, CRI. That's another electrical term. And lamps with high CRI tend to have a natural look no matter what the color temperature. These two terms are explained in more detail later. And this won't take much longer, but I just wanted to show you this is how we make money on selling these light bulbs. And just two more slides and then we'll take a break. The next one is on spectral power. Power. Light is power. Light is energy. Light is matter. Light is everything. So in this slide, spectral power distribution curves is what we call this. They provide the user with a visual profile of the color characteristics of a light source. They show the radiant power emitted by the source at each wavelength or band of light wavelengths over the visible region. In that visible region is 380 to 760 nanometers. You know, that little bitty part of the spectrum. Incandescent lamps and natural daylight, they produce smooth and continuous spectra. I love them. I prefer them. High intensity discharge lamps produce light in discrete lines, HID, or the discrete bands. It's used in spectral analysis to identify or fingerprint the material producing the light. Very good for like operating tables. You can just see everything you need to see. Fluorescent lamps produce a combined spectrum, a continuous or broad spectrum from their phosphor plus the line spectra of the mercury discharge. In general, continuous spectra or very full line spectra produce less distortion of object colors than a few discrete lines. So to view anything, you need to have proper lighting. It's very important. It's not just don't just turn on the light. Sometimes lighting that is not directly on you, we call it indirect lighting. Like this lamp behind me. This one right there, where's my finger? This one right there. It's not indirect. That is shining every which way. Indirect is you cut it off right here and you only shine it on the wall. Just shine it on the wall. What's splashing on the wall. That's it. Alright, so in the next slide you see some spectral power distribution curves of incandescent and cool white. Alright, that concludes part one of two parts of this lecture. That took about 30 minutes. So we'll continue in just a second with a thought question. Alright, break.